All of the models that we've looked at so far in this module, not just neural networks, but also support vector machines and logistic regression and nearest neighbors and AdaBoost, all have something in common. They all are stateless. They have no memory. They are context-free, and they operate in a one-to-one fashion. They take a single, albeit potentially complex and multi-valued input, and they produce a single, again, potentially multi-valued and complex output. Each input is its own thing. It's independent from any that may have come before it, and it has no effect on any that may come after. You put in an X, you get out a Y, and that's it. Lots of things in life are not like that at all. And for many of the problems that we might like to chuck a bit of machine learning at, the data arrives sequentially. The order of arrival is important. The context matters. The past events affect the present. There's some lingering memory in the system. Maybe there's an unknown number of inputs and you need to remember what you've seen before. Maybe there's an unknown number of outputs and you need to remember what you've said already. Maybe both of those things are true. Sequence learning may be relevant to many problems, but probably the most popular and most significant is dealing with language. Language is naturally sequential. Words come after other words. Words themselves may be variable length, and they often have order-dependent meanings and roles. Sentences may be long or short. They may have complicated structure, which refers back to things said earlier in the sentence, or prefigures things that will be said later. They have nested clauses and dangling modifiers. So problems involving language are the ideal problems for the kinds of models that can cope with sequence. So in the examples to come, we will always generally use language, at least somewhere in the problem. That doesn't mean that recurrent networks can only be used for language problems, but it is where they are most commonly and most strongly applied. A feature of sequence learning problems is that there's some kind of decoupling between the input and the output in terms of the quantity of data. So I mentioned variable length inputs and variable length outputs, and both of those are the sorts of cases where sequence learning may be important. These kind of problems may have a number of different forms. For example, a one-to-many problem is one where you would put in a single piece of data of fixed size, and you would get out some number of output sequence elements, and that may be a variable number. An example of this is image captioning. The input to the model would be a single image, but the output would be as many words as the image merits. Conversely, the problem might be many to one. You might have a variable length sequence of inputs, and at the end of it, you emit a single output. An example of this might be sentiment classification. For this kind of problem, you have a piece of text. Let's say it's a review from Amazon or IMDb. It's a chunk of text of unknown length, so you want to read it, say word by word, and at the end you need to give a verdict on whether it's a positive review or a negative review, or is it a real review or is it a fake? As yet a third possibility, the problem might be many to many. And the obvious example here is machine translation. You have an input text in one language, you want to produce a translated text which is somewhat equivalent to the input, but in a different language. Languages can differ quite dramatically in their structure, in the way they perceive ordering, in their verbosity. Some languages might be able to express with a single terse syllable something that in other languages would take a complicated and painstaking paragraph to describe. I've talked about these things as if having variable-sized inputs and or outputs is the be-all and end-all of problems to which you might want to apply a recurrent neural network or a sequence learning approach. This is not necessarily true. It may well be possible that a fixed size problem where you know the size of the input and you know the size of the output may still benefit from being processed in a context-aware fashion. This is not a particularly significant example, but in this week's lab exercises, you'll be applying recurrent networks to images of fixed size, treating them as a sequence of tokens rather than as a grid of pixels. The defining feature of a recurrent neural network, the thing that distinguishes it from the other kinds of models that we've been looking at, is that it has some kind of state or memory. So something gets passed on from processing one piece of data onto the processing of the next. This is what gives it any kind of sequentiality. We can consider this state to be just some hidden internal state that gets quietly updated inside the model, but it's useful, for reasons we'll get to in a few minutes, to consider it instead as an output from the model, which then gets input back into the model at the next time step. However, it's important to distinguish between this internal hidden output, which never really leaves the model, which we call H, and any other outputs that are produced by the model at each time step, the externally visible outputs Y. So these are two distinct outputs. Similarly, at the next time step, the output from the previous time step, H, will be considered as an input into the model at that time, at the new time step. And again, we want to distinguish between that hidden input and the explicit data input that we hand to the model, which is denoted X. If we overlook this doubling up of inputs and outputs with the hidden and the external ones, apart from that, the behavior of our recurrent model is not really very different from the behavior of other neural network models that we've seen so far. In processing data at each step of the sequence, it will have some vector of inputs, it will multiply those by a weights matrix and apply some kind of nonlinear activation function. Classically, for the previous networks we've looked at, this would look like this. In the case of a basic recurrent neural network, the input to this process will in fact be a concatenation of the internal hidden state from the previous time step, which we denote ht-1, and the new input vector from the outside world x t. These will be multiplied by a weights matrix and an activation function. In fact, for vanilla recurrent neural networks, it will be a tan h activation function is applied, and the outputs from this, rather than going directly to the output from the time step yt, instead are saved into the hidden state. So they become the new hidden state, which is passed forward to the next time step. We then generate the actual external output, yt, as a linear transformation of that internal state. This whole process is then repeated across all of the steps of the input sequence. Note that the weights matrices WH, which is used to process the input into the hidden state, and WY, which is used to process the hidden state into the external output, both of those are the same across all of the different steps. There's no change in the weights from the beginning of the sequence to the end. All that changes is the hidden state H. When we start off a sequence at time step 1, the internal state h is initialized usually to zeros. So the operation of this is reasonably comprehensible, although it may not be clear what it's actually doing. But the question that we always come back to with these things is, how do we fit it? Well, as usual, as with other neural networks, we're going to fit it by gradient descent using backpropagation to capture the gradients. We already know how to do this for all of the constituent operations. There's just matrix multiplications and the application of an element-wise activation function, in this case tan h. Still, there are a couple of things that might make you curious and that we should just note. First of all, we don't in any way specify what the hidden vector is supposed to do. It's not directly supervised. The model can use it for whatever it wants. However, it's used to generate the external output y, which is the thing that we can supervise. We have known ground truth values for the y's when we're training. So in combination with the weights matrix wy, there is supervision on the hidden state. Also, since the previous hidden state, ht-1, is effectively an input to the model at time step t, backpropagating into it is essentially the same process as backpropagating into the inputs x from a previous layer at any fully connected layer in a standard multi-layer perceptron. A more substantive concern that you might have about training this kind of model is, how do we backpropagate gradients from the future? At any given time step, we don't know what the gradients from the future will be. However, at training time, we already have all of the data for all of our sequences, and so it isn't really in the future at all. All of the connections from the present to the future, the flow of what we're calling time, are just connections in the graph. We can unroll the whole sequence into a series of separate steps which encompass the whole timescale of the sequence. At each one, there will be inputs that we know and outputs that we know, and we can calculate from the start the flow of values forward through time. At each step, we will know the hidden state and the inputs and the outputs. We can then start at the various outputs, calculate the losses for them, and backpropagate through those, and that will include backpropagating through the time connections from later sequence steps into earlier ones. Just as with the convolutional filter weights in a convolutional neural network, we use the same weights at every point in the sequence. The weights matrices do not change. During backpropagation, all of the unrolled steps will have their own different gradients relating to their own inputs, outputs, and hidden states. And so when we're updating the weights matrix, we need to take into account all of those different gradient contributions. Again, just as with convolutional filters, we use the same approach. We sum over all of the gradients from all the different time steps, and we use that aggregated gradient for each of our weights in order to do the weight update. This process goes by the catchy name of backpropagation through time. In the full version of backpropagation through time, you would backpropagate through the entire sequence, however long that happened to be. But sequences might be very long. So as an alternative, there is what's known as truncated backpropagation through time, where you do the same thing, but you process the sequence a chunk at a time, maybe 10 steps or 50 or whatever. The process runs in exactly the same way. You propagate the data forward through the sequence and through the network, and then you backpropagate the gradients at the end. One difference is that when you go from one chunk of a sequence to the next, you don't reset the hidden state. You propagate the hidden state from the final step of the previous chunk into the first step of the new chunk. However, you don't backpropagate your gradient from the new chunk back into the old chunk. You're already done with the old chunk at this point. There's nothing to backpropagate to. So the gradients only go back as far as each chunk, which means that you're only learning over relatively short term, and it's difficult to learn things that have long-term dependencies. Recurrent neural networks are highly susceptible to vanishing and or exploding gradients because of their recurrence structure. This makes them more susceptible than normal neural networks. The reason is that when you're backpropagating through all the different time steps, you're multiplying along the way as you go, as with any kind of backpropagation. But in this case, one of the factors in that long chain of multiplications will be the weights matrix for the model, and it's the same weights matrix at every step. So you're doing a multiplication of the same thing multiple times. If that thing is bigger than 1, then it will inevitably expand. If it's smaller than 1, it will get smaller. When I say bigger than 1 or smaller than 1, this is actually slightly different criterion in the case of matrix multiplications, but the effect is the same. We're just talking about the singular values of the matrix rather than the matrix itself. In a normal neural network, you're multiplying a long chain of things, but all of those things are different. So there's some scope for evening out big things in one place with little things in another place. That is not available in the case of a recurrent neural network. You're repeatedly multiplying the same thing. Using truncated backpropagation through time helps with this a little bit by just shortening the chain of multiplications. But truncating, as we've already seen, breaks off the possibility of learning long-term effects. So either way, you either cut off the amount of time that you're remembering over, or else you keep it really long, but then you lose it anyway because your gradients vanish. As a result, vanilla recurrent neural networks are not good at learning long-term dependencies. To get around this, we can introduce a different recurrence structure that allows the gradients to bypass some of those bottlenecks. There are a number of different possible candidates for this. We'll briefly look at two. These are LSTMs, or long short-term memory, and GRUs, or gated recurrent units. The LSTM maintains two distinct hidden state vectors, known as the hidden state and the cell state. The way that the recurrence relationship is designed, the cell state doesn't ever participate in long chains of multiplications of the weights vector, and so it is able to keep its gradients for longer and learn and memorize things over a longer term. It could still be subject to vanishing gradients for the normal reasons, though. The recurrence relationship of an LSTM operates through a number of intermediate vectors, all generated from the concatenated hidden state and input vector. These are known as the forget vector, the input vector, the output vector, and the cell state vector, or the gating vector. The equations by which all of these vectors are generated and the way that they combine to generate the new cell state and hidden state look like this. And here is a schematic diagram of the way that they all interact. The important thing is that the operations acting on the C, that's the cell state, do not involve direct multiplication with the weights matrix. So when it comes to backpropagating the gradients through C, they have a relatively unimpeded gradient flow. The LSTM model was first published in the 1990s, and it has been extremely successful ever since. Most of the successes of recurrent neural networks actually use LSTM units rather than vanilla recurrent units. They are a bit more complicated and so a bit more computationally expensive than vanilla units, but they work much better. A more recent adaptation is the gated recurrent unit, which is kind of a cut-down LSTM. It does away with the cell state, but it changes the way in which the inputs are propagated into the hidden state in such a way that it reduces this problem of cascading multiplications with W. The GRU recurrence relations look like this, and this is a schematic of the way that the different components interact within the cell. Gated recurrent units are a bit smaller and a bit less complicated than LSTM units, and consequently they're a bit faster and more efficient to process. On the whole, it seems that on some tasks they can achieve as good a performance as LSTM units. Other times it's not so clear. In most cases, it's worth trying both if it's not too expensive to do so, and seeing if one performs notably better than the other. So far, we've considered only a single-layer recursive neural network, which has its own single set of states, single set of inputs, and single set of outputs. However, it's possible to feed the outputs, the external outputs, from the recurrent neural network into another recurrent neural network layer. In this way, you can build up a multi-layer or deeper recurrent neural network. The outputs from each layer get fed into the inputs in the next. As with other deeper networks that we've looked at, adding layers to RNNs increases their capacity and allows them to learn more complex behaviors. But also, like other deep networks, they will be slower and harder to train and potentially more prone to overfitting. Recurrent neural networks are mostly used for language modeling, but not exclusively. You'll probably have encountered some things that have been produced with the recurrent neural networks. There was that popular game on social media a couple of years ago where they would say things like, "We trained an artificial intelligence on Donald Trump's tweets and look what it came up with." Those kinds of things are almost exclusively done using recurrent neural networks, probably LSTMs. Recurrent neural networks can also be used for more complicated sequence-based tasks, things like generative music or video subtitling. The basic ideas of recurrent neural networks, with some additional added wrinkles, are the basis of very complex, very large language models such as BERT and RoBERTa and GPT, which have been in the news quite a lot lately, and which we'll talk about more in a couple of weeks.